Based on some of your responses in a previous concept engagement, a lot of you were really impressed with that image of planet formation around another star. So I thought we'd talk a little bit more about planet formation around other stellar systems. Of course, we don't have images of what it looked like when planets were being formed in our own solar system. But we can take images now of these protoplanetary disks and see how planets are being formed around other stars. And that gives us a better understanding of what was happening here in our solar system when it was being formed too. So this is the image that you saw previously. This is what we call a protoplanetary disk around the young star HL tau. Now sometimes they're given unusual names, often kind of Greek letters, or sometimes they're named for the survey or particular telescope that observed that protoplanetary disk. So in the middle here would be the star. Surrounding it, we have a disk of material, like our early solar system started from a cloud of gas that contracted in on itself and it spun out to create a disk. The star gets created in the center, and then all around it, you have that flat disk of material. That material is swirling around, and some of those pieces bump into each other, and then they start to grow. They start to accrete, and you start to create planetesimals, baby planets, and then they grow and grow and grow as they move around the dust in the ring, and they collect and gather more mass. And so in these gaps in the ring here, that's where a planet is being formed. So a planet might be being formed out here around this part of that protoplanetary disk, sweeping up that material in its path. Maybe there's another planet being formed here. Maybe there are some planets being formed even much closer into the central star. This distant solar system is 450 light years away from our Earth, and it is found within the constellation of Taurus. The luminosity and temperature of this central star, HL Tauri, indicates that it's less than 100,000 years old. So that's a really young star, a really young star. Our sun is like 4.5 billion years old. It is in its middle ages, and this is really a baby star building its baby solar system. And yeah, the gaps in this ring here are the regions where those planets are being formed, being born around that central star. So that image that we just saw of HL tau was made with observations from a telescope called ALMA, the Atacama Large Millimeter Submillimeter Array. And that image was taken in wavelengths of light that has a wavelength of 1.3 millimeters. So 1.3 millimeters is a much longer wavelength of light than those few hundred nanometer wavelengths of light that we're able to see in the visible part of the electromagnetic spectrum. Now, the ALMA array, the Atacama Large Millimeter Array, is located in the Atacama Desert in Chile. Here we have a map just showing part of, Chile here in South America. And this red dot here is the region where this array of radio dishes or satellite dishes is. This array of satellite dishes can be arranged in multiple configurations, and they can be aimed at a particular part in the sky, and they all kind of work together to create a larger telescope. So because of these long wavelengths of light at which these systems are emitting, that requires massive radio dishes like this to collect light from this part of the electromagnetic spectrum where the wavelengths are very long. Since it's not really part of the visible, well, this is not part of the visible spectrum, we cannot use standard, telescopes that have mirrors inside them in order to gather this light. So you have to use instead these really massive radio dishes that are on, much larger in order to collect that light and focus it toward the center of the telescope. So right here would be the place where they're receiving that information. So the light, just like a mirror in a regular telescope, the light is coming in and it strikes this curved surface, this curved spherical surface. It's not, shiny and reflective like a mirror that we think about, but the surface is enough so that that light, when it strikes that curved dish, reflects and it focuses at one central point right here. And that's where the receiver is, and that's where it's collecting the information from. That's how this telescope is gathering that information. Here are some more ALMA images of protoplanetary disks in different phases of planet formation. So every protoplanetary disk, every solar system that's being built, the disk around that central star is going to look a little bit different. There's different things going on in that disk. There's different amounts of material around that disk. There might be other things nearby in the part of the universe where that planet in that solar system is being built. So here we have, we've got 20 different images of protoplanetary disks, all in different phases of planet formation. So, down here, we've got some well-defined large gaps within the protoplanetary disk. For this particular system, here are also some well-defined gaps. Let's see, up here, these gaps around the central star are less well defined. Here we really only see one of those gaps and then another outer ring. And in some of these systems, we're not looking at the system flat from the front. Those systems might be tilted a little bit with respect to our Earth perspective. So in these systems here, we're kind of looking at that protoplanetary disk more from the side than we are from above. And so we're going to see a different perspective of the planet formation process depending on how these protoplanetary disks are aligned with respect to our Earth position. So for instance, this one down here is a really great example of us looking at one of those protoplanetary disks more from the side rather than from above. If you want to learn more about these images here, you can go to this website, which is where where this data that created this image comes from. Now, these are all images taken by ALMA in the millimeter wavelengths of light, just to look at that protoplanetary disk. But what if we want to actually take an image of the baby planets that are being formed within these gaps in the ring? So to do that, here's the process. In order to take a baby photo of one of those little baby planetesimals that's being built in those gaps in those protoplanetary disks, you have to use a different type of telescope and a different process. So here, this white blob is an image of a planet that is being formed. So this is a baby photo of this baby planet. This planet is called PDS 70b. So the star's name is PDS 70. And the little b here means that that's the first planet that was detected away from the star. So the planet that's closest into the star gets the B, the planet that's next furthest out from the star gets a C, and so on. So here we're looking at the first planet that is closest to the central star, and that's this white blob right here. So how do we take a baby photo of a planet? First, you have to get yourself a really good telescope. Here, they used to create this image the very large telescope in Chile, the VLT, a very creative name. So here's the VLT. You can use each one of these telescopes individually, or you can use them all together to create one bigger telescope. And these are telescopes that do have a regular mirror inside of them. And this image of this for this baby planet was taken in infrared wavelengths of light. So that's still a wavelength of light that's longer than the red colors of light that we can see, but it's shorter than those millimeter wavelengths of light that they use to take the images of the full protoplanetary disks with ALMA. And in order to get a really good image of this planet, what you have to do is you have to block the light from the central star around which this planet is orbiting. And you do that with something called a coronagraph. So a coronagraph is just sort of like a little dot in the center of the telescope that blocks out the light coming from the center star. So here's that little part of the coronagraph that's blocking out the light from the central star. And then that allows us to be able to see the infrared wavelengths of light that are being emitted by the planet. The reason why you have to do this is because the light from that star is so bright, it is going to overpower any light that could come from that planet. And so if you were looking at this system and you didn't block out the light from the light from the star would wash out any signal of light coming from this planet here. So you have to use these coronagraphs to block out the light coming from that star around which this planet is orbiting. And that allows you to get this baby image of this baby planet here. So coronagraphs are something that are also used for the sun, and we can use them for the sun to block out the light coming from the sun's center, and then that allows us to see the sun's corona, which is the sun's outermost atmosphere. And that's where this name comes from, coronagraph. And we'll talk a little bit more about the sun later in the semester. So if you want to learn more about this process and how this baby photo was created of this planet here, there's a nice AstroBytes article about it right here. And this planet, PDS 70b, is orbiting its star at a distance of 22 astronomical units. That's about the same as Uranus's distance away from the sun. So that's about how close this planet is away from its star. And it takes this planet about 118 Earth years to orbit its star. And it is itself just a few times Jupiter in size, and it's known to have a cloudy atmosphere. Jupiter has a cloudy atmosphere. It's got these beautiful bands of clouds in its atmosphere. Saturn has a cloudy atmosphere as well. And if you want to learn more about this particular image and all the science within it, you can read this link. You can go to this link right here, which is an actual copy of the real scientific journal article that was created about this system. Maybe you could go look at it and see, this is what astronomers write to tell other astronomers about their discoveries. This is an example of a journal article that astronomers would create in order to share their data and their findings within the astronomical community. So I thought that you guys would like to see some more information about how planetary systems can be formed. Our solar system is not the only solar system in the galaxy. It's not the only solar system in the universe. There's a lot more planetary systems out there. We have evidence that they exist. We've got all these beautiful images of planets being formed around distant stars. And so it tells us a little bit more about the process that happened in our own solar system as well, 4.5 billion years ago when our solar system was just being formed.